overview for some of the questions that we had on our third midterm exam. So the exam itself, 21 questions that were 4 points apiece that were our short answers. Some of those had partial credit. 5 were open response, scored those at 10 points apiece, and all of those partial credit was possible. If we add up the two different parts, it comes to 134 points. I then scored the exam as a percentage using 130 points. So in a way, that's as if I'm dropping one of the missed short answer questions. And the overall class average was in the low 80s. Within this video, I'm going to discuss responses for the short response. Here I show the questions, the right answers, and the class average on it. So folks did really well, noting that X-ray diffraction was used to determine the crystal structure of solids. Also high scoring was the interactions between adhesive and cohesive forces and capillary action. In order to rise up, we needed to have adhesive forces greater than cohesive. Otherwise, we saw it would not rise upward opposing gravity. If we had cohesive forces being greater than adhesive, our meniscus went in the other direction. Looking at aspects of viscosity. Viscosity is resistant to flow. The largest viscosity would be for our solid, the SiO2 glass. I think that the smallest within here, the one that would flow most easily, would be the 135 hexatriene. I think hexane would have a larger resistance because I see single bonds instead of double bonds, the opportunity for hexane molecules to become tangled up with each other. But I gave partial credit for a decision within that second one. In this feature, it might have been better for me to have this as an open response to hear your reasoning, but that was my reasoning. I'm looking at ionic liquids. I'm looking for ones where I have a cation and anion, and I'm looking for a bulky molecule that will not easily crystallize. So I think C is my best choice with that. I gave partial credit for D, which was also listed as an ionic compound where we had a cation and an anion, where the cation was somewhat more bulky than we'd find with something like NaCl. Given a solid sample, how would you determine if it's a metal or an ionic solid? That was a really high scoring question. Most folks chose aspects of malleability or conductivity and described the phenomena. People did great on that. Also very high scoring was the making a sketch here to consider what would a substitutional alloy look like, what would be an interstitial alloy. Key thing within the interstitial was how we had the smaller substituent within what was otherwise the framework. And for our substitutional, the one that we were substituting in was comparable in size to what we initially had, the host. Silicate structures are built on the SiO4 tetrahedra. Superconductivity is zero electric resistance at very low temperatures. Both of those were quite high scoring. Question 9 here, we have a scenario and we're asked to determine the signs of Q and W. As I look at this, it says the air inside the balloon is the system. During the experiment, the balloon contracts and shrivels up. So I see work being done on the system. The volume of the system is getting smaller as heat is leaving the system. So D is our correct answer for that. I view this as an important topic. So this is one that I'd like you to think through as we head towards our cumulative final exam. To me, this is including the ideas of we have particular scenarios and we're not necessarily doing a calculation, but conceptually we're understanding what does it mean in terms of the heat and the work. And I suppose also the internal energy. We have one about temperature dependence of magnetic materials. As I look at that, I see the first one being described as illustrating antiferromagnetic, where I see the magnetic moment pointing in each direction, in a sense, canceling out. So that would be in region 3. I view the second one as being ferromagnetic, although I understand if folks also considered this to be paramagnetic, but being perhaps aligned in a magnetic field. So I took responses either 1 or 2 as being correct for that. Overall high scoring on that. Very high scoring applying stoichiometry to a enthalpy of reaction data. This is a calorimetry description scenario. This was about 50%. So as we're looking at this for a calorimetry one, here's some students' work. First thing I want to do is look at their thermometer. Temperature goes down, so it tells me it's going to be endothermic. Second, let's determine the amount of heat that's involved. The description here says that we're going to use a specific heat of 4.184 joules per gram K. The grams I will use will be the total amount of the water and what I added to the water. So it's the total mass of the solution. That's what I can use now to determine the amount of heat that's involved. And finally, how do I report it? It's going to be reported per mole of the ammonium nitrate. Partial credit was given for this if the only error was involved in the sign. If you forgot to look at the thermometer and you reported this as negative 26.6 kilojoules per mole, that was partial credit. Other than that, I was looking for the complete work to be correct. Hess's law, pretty high scoring within that. Here's some shown work for how that gets manipulated with the overall enthalpy change then for the target reaction of being 67 kilojoules. Question 4, I think a lot of people had difficulty recognizing what this topic was. So for a standard enthalpy of formation reaction, that's where we're making 1 mole of the product and the elements are coming from their standard states. We can balance it out and fractions would be okay. Partial credit was assigned for this if sulfur was just listed as a single atom instead of this S8 molecule. That was something that was mentioned in class, but I understand where that might not have really caught people's attention. This is one I feel like I didn't do a great job having you practice or stress what a standard enthalpy of formation reaction was. This is a high scoring question on a Chemistry 1210 course because I think the students see it and practice it more. So the low scoring one here I attribute to the recognition on your part, which was dependent on the emphasis or lack of emphasis in my own instruction. Next question right here, pretty high scoring. Partial credit was provided on this. As I read this, here's a reaction. It's described as exothermic, and it's investigated under different experiments. This point right here, if it's at constant volume, I'm noting right away that no work would then be possible. So if I'm thinking about the highest final temperature, if in these other cases, some of the heat is leading to work being done because it's in a piston, and I have a case where there's no work being done, all of the heat's raising the temperature. I like experiment 1 for having the highest final temperature. So that was the first thing I was looking for. Second, as far as the amount of work that gets done, we just said no work was done in 1. And then second, I'm going to say more work is done when it's done reversibly versus irreversibly. So that would be my order. Here we have different scenarios. When it says ignore vibrations in your analysis, tells me right away we've got to be assigning contributions to the heat capacity. And we can then use that to think as we add heat, how does it change the temperature? So for helium gas, constant volume, I'm thinking that there's only translations. For H2 gas and N2 gas, I'm thinking I have 3 translations that would be possible, and then as linear molecules, I'll add in another increment of R. And finally, if it takes place at constant pressure, that gives me another increment of R. So the one that has the largest temperature increase would be the one for the same amount of heat going in that has the smallest heat capacity. That the energy that's being added, the heat that's being added is going entirely into the translations, and that's what the temperature is measuring. So I was definitely looking to see that the greatest temperature increase was for the helium gas. Partial credit was then given for the second portion. The smallest temperature change would be for the H2 gas because that has the largest heat capacity if we look at all the different contributions. That same kind of idea was then applied with these different scenarios. And we again have to think about the heat capacity. the contributions to the heat capacity, they can be added together. In one case, we have only water. Second case, we have more water. And in the third case, we have a combination of water and this metal object. And if we were to look at these, the one that has the largest temperature change is the one where we have the smallest heat capacity. For the same amount of heat going in, if the heat capacity is small, the change in temperature is larger. So A has the largest change, and the one that has the largest heat capacity would be the smallest change, and that turns out to be B. Next one's a scenario involving a heating curve. So as I'm thinking about a heating curve, I'm thinking along the plateaus, the potential energy is changing. I say that because we're adding heat, but the temperature is not changing. So I'm thinking along the plateaus, the potential energy, the arrangement is changing. And we find that within heating curves, we see a longer plateau for the transition when we're going from the liquid to the gas. So that's where the potential energy is increasing the most. If we're thinking about another one, let's say aspect D right here, I think that as the gas increases from 100 to 250, I think my kinetic energy is increasing. That's what the thermometer is measuring, but it's really not changing the potential energy like we see along the plateaus. For the question here involving the, and the Bornhaber, that one, a lot of different ideas were presented there. As I look at it, I think this should have been an open response question. It was not a great question on my part. So the score is really high. There was a lot of partial credit for this. If you're telling me some things that made sense, I tried to give full credit for this one. Back to the idea of a heating curve, that's an important topic for us. It's an important topic because it includes a lot of different ideas that we're seeing coming together, including aspects of particle motion. What does it mean in terms of the structure of the solid or the liquid? And we're even finding that this connects now to ideas involving entropy. So this is an important topic for us. Question 20 is a conceptual one that I tried. The empty space that we have within an atom, if we just consider the size of the nucleus relative to the size of the electrons and then the volume that it would be found in, a lot of empty space. The amount of empty space that we have within a solid, we've seen that might be on the order of 50%, 60%, depending on what our structure is, but it certainly pales in comparison to the amount of empty space within the atom itself. Like I said, this was sort of a conceptual question, and I was just curious to see how it would work for us. The last one, if we're thinking about state functions, we've seen and deliberately stated how enthalpy and internal energy are both examples of state functions. We also contrasted that how heat and work were not state functions. So I was looking for that piece of information first. Partial credit was then whether how people made sense of pressure and volume. Pressure and volume are both state functions. Imagine, let's say we're looking at volume, and you got a balloon, and it has an initial volume, okay? And then let's say the volume increases, and then the volume increases more, and then it decreases, and then it increases. And you're asking the question, let's compare the initial and final volume. The initial and final volume, it doesn't depend on the path at all, right? Whether it got really big and then got smaller again, or it went in different steps, volume, pressure, both examples of state functions.